177 milliseconds. Our switch is not great, so there'll be small errors, but we can make do with those. Yeah, around 177 milliseconds average is what we're getting. Today we'll look at the equation that predicts displacement for a body under constant acceleration. The equation goes S is equal to ut, where u is the initial velocity and s being the distance, plus half at square. A is the acceleration and t is the time taken. So here, if the initial velocity is 0, then the equation reduces to s is equal to half at square. Now in this experiment, we're going to use an object and let it free fall through a certain distance. Now we'll know what this distance is because we'll measure it physically, and we'll also use the Seelab device to precisely measure the time taken for this body to travel from point A to point B. Now since this is a very fast process, couple of 100 milliseconds, and the object is going to hit the ground, we're going to need some tools to make this automatic. First, we need to choose what the object is and how we're going to release it. So I'm going to use a metal ball. This is an MS steel ball, and one of these relay modules which have a solenoid inside. And what I'm going to do is I'm going to cut up this relay and just expose the solenoid, and then use the Seelab device to somehow attach this ball to the solenoid. So this way the Seelab can programmatically release this ball so that it can start a timer when this ball is dropped, and then it'll stop the timer when a certain input is triggered. So let's see how we can do that. So broken off the top of the relay, and what you see is the solenoid. So it has 3 connections to be made: plus, minus. One goes to 5 volts, minus is ground, and S, which is a signal pin used to control the nature of the solenoid, whether it's on or off, and that will go to OD1. So let's do that. You should be able to see that I've made these connections. I've taken 5 volt and ground from here and connected it to the relay, and the signal pin goes to OD1, which is here. Now I'm going to start the experiment here. So under the experiments, you have time of flight gravity measurement, and this gives you a few controls. First is you can toggle OD1. You see, when I turned on OD1, the red light on the relay turned on. See, that means the electromagnet is energized. Now how do we find that out, whether it's actually energized? Let me just take this MS ball, make this parallel to the ground, and stick it there. So there, it's holding the ball, and in order to release it, all I need to do is turn off OD1 and the ball falls. If I turn it on again, I can attach it there. Right? Now the second step is to figure out when the ball hit the ground. In order to do that, we have a small contact switch like so. So this contact switch is your input. When SEN gets connected to ground, that's when the device knows that this ball has hit the ground. So how do you do that? So in order to do that, I'm going to use a couple of alligator clips, connect one to ground and the other one to SEN. So whenever these two clips come in contact, the SEN input goes low, as can be observed in the graph. You see, the value of SEN is now 0 volts if they're touching. If not, it's 3.3 volts, and the graph tells you that things are actually working. So this graph is valid only when timing measurements are not being made, and it helps you figure out whether your setup is correctly configured or not. And there are many ways in which you can make a contact switch such that the switch comes in contact with the clips, come together whenever the ball hits it. But we're going to make a very simple thing. We're just going to use a metal foil and wrap it around a piece of cardboard. So I have this foil wrapped around this little playing card. So I have a large metal surface on which I hope the ball will drop. And what I'm going to do is I'm going to put the clip on one side of it. So I have one clip here. So here I have a very crude switch. So this foil is actually not touching this, but whenever something will fall on it, you can see from the graph that it actually works as a crude contact switch. This should be sufficient for our little simple demo. And we'll come to the final part, which is the timing button here. So when you click the timing button, OD1 will toggle its state. So if it was high, it will become low, or vice versa. And a precise timer with sub-microsecond accuracy is going to start measuring the time. Now when does the timer stop? It stops when this sen sees a level change. So right now it's at 3.3 volts. A level change would mean it would go to the other side, that is 0 volts. So let's just try it out manually. Started the timer. Wait. Yeah. So you see, it has a timeout of a second or two. So the moment you hit it, the ball is going to drop because the relay is off. So whenever the ball hits it, the timer will stop. Now let's do the actual experiment. I will attach the ball here. Our switch is ready, and I will click on timing. 178 milliseconds. Let's try that again. 177 milliseconds. Our switch is not great, so there'll be small errors, but we can make do with those. Yeah, around 177 milliseconds average is what we're getting. Let's now measure the distance traveled with this ball. So I have a ruler here. I'll take it to the surface that it hits and the bottom side of this ball. So that's around 15 centimeters. So here I have 15 centimeters. Now in the equation S is equal to half AT square, if we know 2 out of 3 variables, we should be able to figure out the third variable. So let's see if we can plug in the value of gravity as 9.8 and the value of time, what we measured, whether or not we get the distance that we just measured with our scale. So S is equal to half into value of gravity, that's 9.8 meters per second square, into t square. T is 0.176 seconds into 0.176, which comes us a value of 15.17 centimeters, which is quite close to what we measured. In fact, if we measure it even better, instead of just a crude scale, we might even come even closer to the value. I think we can conclude now. Thank you.